Hello and welcome to Random Topics with Jack, the podcast where we explore the intriguing and sometimes controversial topics that shape our understanding of the world. Last time we were looking at mass transit, the systems that move millions of people through towns and cities. This time, we're looking at technology that can power those cities by doing something both astonishingly strange and surprisingly familiar. Nuclear power, which is an extraordinarily complicated way to boil water. And that description is completely accurate. But it is also a bit like describing a space launch as an elaborate method for making something go up. The steam matters, but the interesting part is where the heat comes from, how the reaction is controlled, what happens after the fuel has been used, and what society is willing to accept in return for large amounts of low-carbon energy. Nuclear power is one of those subjects where people often arrive with a conclusion already assembled. To some, it is clean, dependable, and essential. To others, it's expensive, dangerous, and inseparable from accidents and waste. Both sides can point to real evidence, but both sides can also turn a complicated engineering and political question into a slogan. So this is neither a sales pitch nor a horror story. We're going to begin inside the atom, follow the energy through a power station and out to the grid, and then keep following the consequences through accidents, exclusion zones, spent fuel, economics, and the choices facing the UK in particular. Along the way, we will answer a few deceptively simple questions. What actually splits? Why does a reactor not behave like a nuclear bomb? What does scrams stop, and what does it not stop? What can Chernobyl and Fukushima teach us about without pretending they were the same accident? And when somebody says nuclear power is either obviously necessary or obviously obsolete, what information are they actually leaving out? So that is our route. Atom, reactor, turbine, safety systems, aftermath, waste, climate, cost and choice. Let's get started. So the word nuclear refers to the nucleus, the tiny, dense centre of an atom. Most of an atom is occupied by its electrons in the space in which they move. But almost all of its mass is contained in the nucleus, where protons and neutrons are held together. Chemical reactions rearrange electrons. Nuclear reactions change the nucleus itself. And that distinction matters because the forces and energies involved are very different. Commercial nuclear power stations today use fission. Fission means splitting a heavy atomic nucleus into two smaller nuclei, along with a few free neutrons and a large release of energy. Fusion goes in the other direction. It combines light nuclei, usually forms of hydrogen, to make a heavier nucleus. Fusion powers the sun, and experimental machines on Earth are trying to make it a practical energy source. But fusion is not what's happening in the nuclear power stations currently connected to our electricity grids. They use fission. You may also have heard of cold fusion, the claim that useful fusion could occur in relatively ordinary laboratory conditions, rather than the immense temperatures used in conventional fusion research. The term became famous in 1989 when Martin Fleischmann and Stanley Pons announced that in an electrochemical experiment, it appeared to produce excess heat from a nuclear process. Other labs could not reproduce the claimed effect reliably, and reviewers found no convincing, repeatable evidence that cold fusion had been demonstrated. Researchers have revisited related ideas under names such as low-energy nuclear reactions, including a major Google-funded effort published in 2019. And that work did not find evidence of cold fusion either, so cold fusion is not an established energy technology. It is, however, an excellent story about scientific replication, publicity, uncertainty, and what counts as convincing evidence, which is why I'm leaving most of it for a full episode on its own down the line. But for today, the important distinction is simple. Fusion joins light nuclei, fission splits heavy ones. And the electricity produced by present-day nuclear power systems comes from controlled fission. So, what is the fuel? Well, the usual short answer is uranium-235. The answer is useful, but it does need a footnote. Natural uranium is mostly uranium-238. It's only about 7 atoms in every 1,000 are uranium-235, the isotope that readily sustains a chain reaction with slow neutrons. Most commercial reactor fuel is therefore enriched so that the uranium-235 makes up a few percent rather than less than 1%. The uranium is normally formed into small ceramic pellets. Those pellets are stacked inside sealed metal tubes called fuel rods. The rods are arranged into fuel assemblies, and the assemblies make up the reactor core. But uranium-235 is not the only fissile material that can be used. Inside an operating reactor, uranium-238 can absorb a neutron and through a sequence of radioactive changes become plutonium-239. Some of that plutonium then fissions inside the same fuel and contributes to the energy being produced. Plutonium-239 and plutonium-241 can also be deliberately mixed oxide fuel, usually called MOX, where plutonium oxide is mixed with uranium oxide. Another possible fuel is uranium-233. It can be bred from thorium-232 and has been used experimentally, including in the shipping port reactor in the United States. That does not mean a thorium reactor can be fueled with a lump of thorium and switched on. Thorium-232 is fertile rather than fissile, and it can be converted into fissile uranium-233, but does not normally sustain the same kind of thermal neutron chain reaction by itself. Uranium-238 is also described as fertile for the same reason. It can become useful fissile material after neutron capture, but that extra step matters. So if we say reactors usually use uranium-235, the two most useful alternatives to remember are plutonium in MOX fuel and uranium-233 bred from thorium. There are more possibilities, especially in fast reactor and advanced fuel designs, but we do not need to collect entire actinide Pokédex today. The important point is that reactor fuel is not one element with one behaviour, it is an engineered mixture of isotopes chosen to produce a controllable reaction. So now that we know this, we can follow one fission event. A neutron enters uranium-235 nucleus. The nucleus absorbs it, becomes unstable and splits. Two fragments fly apart at high speed, more neutrons are released, and a small amount of mass becomes energy, following Einstein's relationship between mass and energy, E equals mc squared. Most of the useful energy begins as the motion of those fission fragments. They crash into the surrounding fuel material that transfer that motion as heat. So the reactor is not producing electricity directly, it's producing heat. The extra neutrons create the possibility of a chain reaction. One fission can trigger others. Those fissions trigger more. The job of the reactor is to keep that multiplication balanced. If too many neutrons disappear without causing another fission, the reactor is subcritical and the next chain reaction falls away. If each generation the fission produces on average is exactly enough useful neutrons to sustain the next generation, the reactor is critical. In nuclear engineering, critical does not mean everyone should run from the building. It means the chain reaction is steady and self-sustaining. If a neutron population is increasing, the reactor is supercritical. That can be normal part of gradually raising power provided the rate is controlled. Reactors manage the balance in several ways. A moderator, often ordinary water, slows neutrons, making them more likely to cause fission in uranium-235. Control rods contain materials that absorb neutrons. Insert them further and fewer neutrons remain available. Withdraw them and more remain. Some pressurized water reactors also use dissolved boron in the coolant to help control longer-term reactivity. The fuel composition, geometry and coolant temperature, as well as reactor design, all affect the chain reaction as well. This is why a power reactor is not a nuclear weapon waiting to happen. The fuel is far less enriched, the geometry is different, and the system is designed to sustain a controlled release of heat rather than assemble an extremely rapid, uncontrolled chain reaction. A reactor accident can still produce explosions, but steam pressure, hydrogen, and burning material is not the same thing as a nuclear bomb detonation. That distinction will matter when we reach Chernobyl and Fukushima. There are many reactor designs, but we need one clear example. So let us use a pressurized water reactor, or PWR. The reactor core sits inside a heavy steel pressure vessel. Water flows through the core and carries away the heat. The water is kept under high pressure so that it remains liquid even at temperatures where it would normally boil. It belongs to the primary circuit. The hot primary water passes through a steam generator where it transfers heat across metal tubes to a separate supply of water. That secondary water boils. The steam expands to a turbine. The turbine turns a generator. The generator moves electrons through the grid. After leaving the turbine, the steam reaches a condenser where another cooling system removes waste heat and turns it back into liquid water. Then the secondary cycle begins again. Core, primary coolant, steam generator, secondary stream, turbine, generator, condenser, and back again. The separate circuits are important. In a PWR, the water that passes through the reactor core does not normally pass through the turbine. Heat crosses the barrier inside the steam generator, but the two bodies of water remain separate. Other reactors arrange this differently. A boiling water reactor produces steam inside the reactor vessel and sends that steam towards the turbine. Britain's advanced gas-cooled reactors use carbon dioxide gas to carry heat from the core, while their fuel is moderated by graphite. Different plumbing, same broad conversion. Nuclear energy becomes heat, heat makes steam, steam spins machinery, machinery makes electricity. And those enormous concrete cooling towers that have become visual shorthand for nuclear power, they're part of the waste heat system, not the reactor. The white plume is mainly condensed water vapour, not smoke and not a cloud of radiation. Cooling towers are also used by some coal, gas and industrial plants, and not every nuclear station has one. The reactor may be unusual. The turbine hall may look much more familiar to any conventional power engineer. So suppose a plant needs to stop the chain reaction quickly. The reactor trips. In American usage, this is often called a scram. You may have heard that scram stands for Safety Control Rod Axeman. That expansion comes with a genuinely excellent story. During the first controlled self-sustaining chain reaction at Chicago Pile 1 in 1942, physicist Norman Hilbery stood ready with an axe. If necessary, he could cut a rope and allow an emergency control rod to drop into the pile. The Axeman was real. The acronym? Probably not. The US Nuclear Regulatory Commission's historian has traced Safety Control Rod Axeman as a later backronym, words fitted to create an existing term after the fact. Scram was already slang for getting out quickly. So use scram as the name for a rapid reactor shutdown and enjoy the axe swinging story without presenting the phrase as settled etymology. In a modern reactor, a trip rapidly inserts control rods or otherwise adds neutron-absorbing material. The sustained fission chain reaction collapses, but the reactor does not instantly become cold. Fission products inside the fuel remain radioactive. As they decay, they continue to release heat. That's called decay heat. It falls with time, but immediately after shutdown, it is still substantial enough that cooling must continue. This gives us one of the most important sentences in the episode. A scram stops the chain reaction. It does not stop radioactive decay. That's why shutdown systems and cooling systems solve different problems. It's also why backup electricity matters. Pumps, valves, instruments, and control systems may be needed after the reactor has stopped generating power. Plants therefore use multiple sources of electricity. Emergency generators, batteries, procedures intended to keep cooling available even when parts of the system fail. Newer designs may also use passive safety features that rely more on gravity, natural circulation, or stored pressure and less on active pumps. None of this makes failure impossible. But what it does mean is that the plant is designed around the expectations that individual components can fail. The larger safety question is whether enough independent layers remain when failure arrives together. So nuclear safety is built around defense and depth. Instead of trusting one flawless machine or one flawless operator, designers create layers. The ceramic fuel retains much of the radioactive material. Metal cladding surrounds the fuel. The primary pressure boundary contains the coolant. A robust containment structure surrounds the major reactor systems in many designs. Monitoring, shutdown and cooling systems add further layers. Procedures, training, regulation and emergency planning sit around the engineering. The idea is that no single fault should immediately become a public disaster. Redundancy provides more than one way to perform a vital function. Diversity tries to prevent identical equipment from failing for the same reason. Physical separation reduces the chance that one fire or flood disables every backup at once, and regulators require operators to demonstrate that the plan remains within defined safety limits. 3 related words are worth separating here. Safety means preventing accidents and limiting their consequences. Security means protecting facilities and materials from theft, sabotage, or attack. Safeguards means verifying that civil nuclear materials are not being diverted towards nuclear weapons. They overlap, but they are not synonyms. A plant can have excellent industrial safety procedures but still need stronger security. A country can operate safe reactors and still face international questions about enrichment or reprocessing. And safeguards are not a guarantee that nothing will ever go wrong inside the plant. They answer different risks. The same is true of radiation. Radiation is not a single magic substance. Risk depends on the type of radiation, the dose, the route of exposure, and how quickly the dose is received and which tissues are exposed. That complexity can be abused in 2 directions. It can be used to dismiss every concern as irrational, or it can be flattened into the idea that any detectable radiation means catastrophe. Good risk communication does neither. It explains the exposure, the uncertainty, and the comparison being made. Nowhere is that more important than in the history of nuclear accidents. 3 Mile Island, Chernobyl, and Fukushima are often grouped together as natural nuclear disasters, and that is understandable, but it's too vague to teach us very much. 3 Mile Island, Unit 2 in Pennsylvania, suffered a partial core meltdown in 1979. A pressure relief valve became stuck open while indicators in the control room design made the plant's condition difficult to understand. Operators reduced emergency cooling because they misread what was happening. Fuel was badly damaged, but the reactor vessel and containment limited the release. The accident caused no immediate death or injuries. The official assessments found that the small off-site radiation exposures were not expected to produce detectable health effects. The lesson was not that a meltdown is harmless, it was that human-machine interfaces, training and containment are part of safety engineering. Chernobyl Unit 4 in 1986 was a radically different event. The RBMK reactor had hazardous characteristics at low power. During an unsafe test, protections were disabled and operating conditions became unstable. A sudden power excursion caused explosions and a fire in the graphite moderator. The reactor lacked a Western-style full containment structure, allowing large quantities of radioactive material to escape. Workers and firefighters received enormous doses. Some died from acute radiation syndrome, and radioactive iodine exposure caused a large increase in thyroid cancer among those exposed as children or adolescents. The wider long-term health burden is more difficult to quantify and is still surrounded by disputes over dose reconstruction statistics and which effects can be attributed to radiation. But the destruction of the reactor, the emergency deaths, the thyroid cancers, and the displacement of communities are not in doubt. Then came Fukushima Daiichi in 2011. The reactors that were operating shut down automatically after the earthquake. That part worked. The tsunami then flooded the electrical equipment and disabled much of the power and cooling capacity. Heat decay continued. Fuel overheated and cores were damaged. Hydrogen accumulated and exploded in reactor buildings. Radioactive material was released and large areas were affected. UNSCEAR reports that no adverse health effects among Fukushima residents have been documented as directly attributable to radiation exposure, and it does not expect future increases to be detectable. That conclusion should not be twisted into nothing happened. The earthquake and tsunami killed thousands of people. Evacuation disrupted medical care, displacement, stress, lost livelihoods, and years of uncertainty caused a serious non-radiological harm. The fair comparison is not a contest for the scariest photograph. 3 Mile Island shows the value of containment and the danger of confusing controls. Chernobyl shows how hazardous reactor characteristics, rule breaking, and weak containment can combine. Fukushima shows why a successfully stopped chain reaction still requires resilient cooling, power, and emergency planning. Different designs, different initiating events, different releases, different health and social consequences. But accidents are not finished when the fire is out. They come through land, infrastructure, law, memory, and the lives of people who cannot simply return to normal. The Chernobyl exclusion zone is one of the clearest examples. Pripyat and many surrounding communities were evacuated. Land use was restricted. Radiation had to be mapped and monitored. Forests, soil, food, and water became long-term management problems. The familiar 30-kilometre zone is only shorthand. Fallout did not politely stop at a circle. Weather and landscape produced uneven contamination across Ukraine, Belarus, Russia, and other parts of Europe. Inside the zone, the new safe containment now covers the remains of Unit 4, while decommissioning and radioactive waste work will continue for decades. The zone has become an ecological reserve. With most farming, construction, traffic, and hunting removed, forests expanded and populations of several large mammals became conspicuous. That is scientifically fascinating, but it does not prove that radiation is harmless. Wildlife is responding to two things at once: continuing radiation exposure and the enormous reduction in ordinary human pressure. Different species, tissues, and locations also receive different doses. The useful lesson here is not that nature has defeated radiation. It's that ecosystems can change dramatically when one major stressor, human activity, is removed while another remains. And since the full-scale invasion in 2022, security conditions along the Belarusian border have created an additional obstacle to reopening parts of the zone. That's enough war context for this episode. The focus remains on the long aftermath after the nuclear accident. Fukushima created a different recovery landscape. Japan designated special decontamination areas where the national government took responsibility for cleanup. Work included removing contaminated soil, cleaning buildings, managing vegetation, monitoring radiation, and storing enormous quantities of removed material. Evacuation orders have been lifted in stages as infrastructure and conditions have changed. Some difficult-to-return areas remain, and legal permission to return is not the same thing as restoring a community. Schools, shops, health services, jobs, neighbours may no longer be there. Some residents want to return. Some do not. Some cannot. Putting Chernobyl and Fukushima beside each other shows why aftermath cannot be measured by a radiation reading alone. It includes contamination, cleanup, and exposure. It also includes those who were displaced, what was lost, and whether a place can function as home again. And the reactor is one stage in a much longer fuel cycle. At the front end, uranium ore is mined and milled and concentrated into a concentrated material commonly called yellowcake. It is converted into a chemical form suitable for enrichment. Enrichment increases the proportion of uranium-235, the uranium converted again, manufactured into pellets and assembled into fuel. After several years in a reactor, the fuel contains fission products, remaining uranium, newly formed plutonium, and other radioactive elements. It is now spent fuel. Spent means it's no longer convenient to use in that reactor in its current form. It does not mean that the material has stopped being radioactive or producing heat. Freshly removed fuel is stored underwater. The pool cools it and provides radiation shielding. After enough time, fuel can be transferred into dry casks made from steel and concrete. From there, countries make different choices. Some treat spent fuel as waste intended for direct disposal. Some reprocess it to separate uranium and plutonium for possible reuse. Reprocessing can recover useful material. It does not make the waste disappear. It changes its form, creates additional waste streams, costs money, and raises security and proliferation questions. Radioactive waste is usually divided into categories such as low level, immediate level, or high level, although exact definitions vary by country. Low-level waste includes things such as contaminated clothing, filters, and tools. Higher activity waste contains much greater concentrations of radioactive material and may produce heat. One of the nuclear power's genuine advantages is that the physical volume of its most hazardous waste is relatively small compared with the enormous flows of fuel and air pollution associated with fossil power. One of its genuine disadvantages is that this small volume needs careful isolation over timescales far longer than a power company or government term. Deep geological disposal aims to place the waste within multiple engineered barriers in stable rock far below the surface. The physics is understandable. The hard part is not only geology, it's building public trust, choosing a site, defining consent, funding the programme, and maintaining institutions long enough to finish it. Britain's geological disposal facility programme is still searching for a willing and suitable host community. And the waste is not the only long tail. Reactors eventually need decommissioning. Systems must be defueled, dismantled, packaged, monitored, and the site moved towards another use. And that can take decades. The honest position is neither the waste problem is solved or there is no possible solution. We know how to package, shield, monitor, and isolate radioactive material. The unresolved questions are where, when, and at what cost, and with whose consent. Nuclear power produces very little carbon dioxide while the reactor is operating. Across the whole life cycle, mining, construction, fuel processing, operation, and decommissioning, it is low carbon rather than literally zero carbon. Major assessments place its life cycle emissions in the same broad low carbon group as wind power and far below unabated coal and gas. That gives nuclear power a serious climate argument. Reactors can produce huge amounts of electricity for long periods in almost any weather. They can reduce dependence on fossil fuel generation and provide firm capacity when wind and solar output are low. But low carbon is not the end of the analysis. Nuclear plants need construction materials, supply chains, skilled workers, cooling, and a functioning grid. They can be affected by heat waves, drought, coastal hazards, or limits on how warm discharge cooling water may be. And an electricity system is not a competition where one technology must eliminate all the others. Wind, solar, nuclear storage, demand flexibility, interconnectors, and dispatchable generation solve different parts of the problem. The useful question is what combination can deliver reliable, affordable, and low-carbon power in a particular place. Cost is where nuclear debates become especially slippery. An existing reactor and a new reactor are not the same investment. Keeping a safe existing plant running can preserve a large amount of low-carbon generation without rebuilding it from scratch. A new large reactor requires an enormous amount of capital before it sells its first unit of electricity. Interest accumulates during construction. Delays raise financing costs. First-of-a-kind engineering changes can multiply risk. On the other hand, once operating, a reactor has a relatively low fuel cost, a long potential life, and high output. Levelized cost of electricity tries to spread lifetime costs across lifetime generation. It's useful, but incomplete. It may not capture the grid value for producing power at a particular hour, the cost of backup and transmission, the benefit from firm low carbon capacity, or the financial damage caused by construction risk. So anybody offering one cost number should be asked several questions. Is there an existing plant or a new build? Who pays if it's late? What interest rate is assumed? How long will it operate? What system costs are included? What would replace it? Nuclear power can be climate relevant and economically difficult at the same time. They're not contradictory statements. And the UK itself is trying to manage this awkward transition. Most of its operating nuclear fleet consists of aging, advanced gas-cooled reactors approaching retirement. Sizewell B is the country's only operating pressurized water reactor. Hinkley Point C is under construction in Somerset. Sizewell C is intended to repeat much of that design in Suffolk. The UK government has also selected Rolls-Royce SMR as the preferred bidder for National Small Modular Reactor Programme. The ambition is clear: replace retiring capacity, support energy security, and retain nuclear engineering skills. The delivery challenge is equally clear. Large projects take years, carry financing risks, and can arrive later than the electricity system originally expected. Scotland makes the question more politically visible. Torness remains the country's operating nuclear station is currently expected to generate until 2030. subject to continuing safety cases and inspections. The Scottish Government opposes the construction of new nuclear fission stations using current technologies. Supporters of that policy point to cost, waste, construction times, and Scotland's renewable resources. Critics point at the loss of firm low carbon generation, skilled employment, and difficulty of balancing a highly renewable grid. The argument is sometimes presented as nuclear versus renewables, but that's far too simple. The real comparison includes storage, transmission, interconnection, demand, backup generation, construction schedules, and the carbon budget during the transition. It also includes democratic choices about which risks a country is prepared to own. A wind farm changes landscapes and needs grid connections. Gas provides flexible power but emits carbon unless emissions are captured. Large nuclear plants concentrate costs and construction risk. Long-duration storage is promising but not yet available everywhere at the necessary scale. There's no energy system made only from benefits. There are systems whose trade-offs are visible in different places at different times. The UK's question is therefore not simply whether nuclear power is good, it is whether particular projects can be built safely, financed credibly, and delivered soon enough to outperform the realistic alternatives. The Scottish question is what combination replaces Torness while keeping electricity reliable and emissions falling. Those questions deserve numbers, dates, contingency plans, not identity badges. The phrase small modular reactor covers several ideas. Small refers to electrical output relative to traditional gigawatt scale reactor. Modular means that major components may be manufactured in factories and assembled in repeatable units. The promise is a lower upfront commitment, simpler construction, and learning through repetition. But a smaller reactor does not automatically produce cheaper electricity. Large reactors benefit from economies of scale. Small reactors need economies of manufacturing and repetition to compensate. That means the first projects matter enormously. They have to prove that designs can be licensed, factories can produce them consistently, and enough orders exist to create a genuine series rather than a collection of expensive prototypes. Advanced reactors include fast reactors, high-temperature gas reactors, molten salt concepts, and other systems sometimes grouped under Generation 4. They may aim for higher temperatures, different fuels, passive safety behaviour, and more efficient use of uranium. Some could consume materials that current reactors use less effectively. Some could provide industrial heat as well as electricity. But advanced is a goal, not evidence that a project has solved material science, maintenance, regulation, economics, and/or waste. Thorium belongs in the same category of careful optimism. It's abundant, and breeding uranium-233 from thorium can support useful reactor cycles. That does not remove the need for a fissile starter material, chemical processing, radiation protection safeguards, waste management, or a commercially proven design. Thorium is an option. It is not a magic word, and fusion remains separate. Experimental fusion has made important scientific progress, but is not currently supplying commercial electricity to the grid. It should be researched because the potential is enormous. It should not be used as an excuse to postpone decisions about the power system we have to build now. The future of nuclear power will probably be less dramatic than either side predicts. Not a universal atomic age and not an automatic disappearance. Some countries will extend existing plants. Some will build large reactors. Some will test smaller advanced designs. Some will reject new nuclear and build around other resources. The results will depend as much on institutions' financing and construction discipline as on the reactor physics. So nuclear power begins with nucleus splitting, fission, fragments transfer their energy to heat. Heat moves through a coolant, steam turns a turbine, a generator supplies the grid, but the full system is much larger than a reactor. It includes mines, enrichment plants, fuel factories, cooling systems, operators, regulators, emergency plans, waste stores, communities, and decisions that last longer than the people who first made them. Uranium-235 is the usual headline fuel, but plutonium can contribute or be used in mixed oxide fuel, and uranium-233 can be bred from thorium. Critical means steady, not catastrophic. A scram stops the chain reaction, but decay heat means cooling must continue. Defence in depth does not promise that accidents are impossible. It tries to prevent one failure from becoming many. 3 Mile Island, Chernobyl, Fukushima demonstrate different combinations of design, natural hazard, equipment, information, and human action. Their aftermaths also remind us that consequences are physical and social. Radiation dose matters, so does evacuation, lost homes, interrupted healthcare, contaminated land, and decades of uncertainty. The Chernobyl exclusion zone can be both contaminated land and an ecological reserve. Fukushima can now have low radiation health effects, but still have communities living through profound disruption. Nuclear waste is compact, hazardous, and technically manageable. It is also politically and institutionally demanding across very long timescales. Nuclear electricity is low carbon and capable of steady, large-scale output. New nuclear projects can also be slow, capital intensive, and vulnerable to decay, which brings us back to the debate. Is nuclear power safe? Compared with what design, under what regulation, and against which alternative? Is it affordable for an existing station, a first-of-a-kind mega project, or the 10th repeated unit? Is it necessary? Oh, in which country, with which grid, resources, climate targets, and construction capacity? There's no single answer hiding behind the cooling towers. There are particular reactors, particular places, particular timescales, and particular choices. The most useful position is not automatically pro-nuclear or anti-nuclear. It is pro-specificity. Tell me the design, tell me the site, tell me the safety case. Tell me the schedule and who carries the risk. Tell me what happens to the waste. And tell me what we build instead if the reactor is not built. That is where the real argument begins. But next time, we're leaving power stations behind and looking for life beyond Earth in astrobiology. How would we know if we found alien life? Because finding something strange is one challenge. Proving it's alive and not contamination, chemistry, or an overexcited press release, that's another. As always, I've been your host Jack, and until next time, please do keep questioning and exploring.